This meeting is being recorded.
Okay, so welcome everybody to today's talking seminar. Our speaker today is João Pedro dos Santos, and he will speak about the differential Galois theory over a discrete valuation ring. Please.
So let me start by thanking you very much for this invitation to participate in this very nice and seminar. So I will talk about this work that I've been doing for last decade with my colleague Hai from Vietnam and his students. And so the main problem is to do differential Galois theory in the case where the objects, the modules and connections and differential equations are defined over something other than a field. And mostly the results will deal with discrete valuation rings. So, okay. So let me start with the introduction of usual Galois theory from a Tanaka viewpoint, because at the end what you realize is that if you're going to do things over which are not over field, then you're going to need some more categorical machinery and algebra. So if you try to do the Picard-Vicieux theory, you run into some problems. So let me just recall, so I'm sure most of you know this thing, but maybe you don't do that every day, so I'll give you a quick presentation. So I take a field and I take some category, which is K-linear. So K-linear category is just some category where you are allowed to multiply things, morphisms by scalars. So the morphisms between two objects are just vector spaces. And then you have a functor, which is the tensor product. And the tensor product, of course, it's assumed to be ACU, which means associative, commutative, and has a unity. Okay, so I'm dealing exclusively with the commutative case, which is the one interests me. And then I have this condition, which is the existence of jewels. So it means that basically there's an object which will have a trace and a co-trace, and these shall satisfy the usual properties of a dual vector space. Okay. So, and at the end, I also suppose that my category can be embedded into the category of vector spaces and all compatible with the tensor product, right? So this means that T at the end of the day is just a category of vector spaces, and all these constructions are respect the constructions you do usually in vector spaces. But since this last condition on the embedding property is not universally accepted, you know, some people make a living out of suppressing this condition, and so this last one is not the right one, but for me it's okay. So then, once you have this data, you have this very famous theorem going back to Saavedra, and it says that if you have such a category, what you have really is that your category is the category of representations on some group scheme, affine group scheme. So if you're not used to affine group schemes, so you're better off just thinking of these as projective limits of linear algebraic groups. Okay, so it's a simpler way, and all affine group schemes are projective limits of linear algebraic groups. Okay. Well, you have to take linear in a more subtle sense than just reduced, but okay. So let me restrict myself. And in addition, what this key property here says that if it just happens that every object on T is a subquotient, so it's a quotient of a sub-object of some tensor power, okay, so you have E and you have some tensors, okay, so say that you have these guys here, and every object V is a quotient of one of these guys, then I can say that V, the E here, okay, since I have this equivalence, it's just a representation of pi, and the representation given is just a closed embedding. So it means that if your category is generated by one object, then your group is algebraic, finite time. So it means that you don't really have a projective system, you just stop at some point. Okay. So the example of why I'm doing this is of course the category of connections on the affine line, minus the number of points, okay? So very simple object to start with. And well, I turn on the machine and I pick myself a point, and I have myself this functor psi, which associates to any differential equation, right? So connections just means that I take a coherent sheaf, or if you're better, more used to taking a module over the ring of functions, which happens here. Okay, so this is an affine space. So you just take a module over these guys, and you pick a point, and then you consider the map, the functor, which sends every equation to its fiber over psi. Okay. So once I do that, I turn on the theorem, I employ the theorem, and I get this equivalence. So this is pretty much as in Galois theory, where you have that the absolute Galois group of some space, which is very difficult to study, although some people can do that, but that's usually very difficult. And you have this equivalence between the category of connections all over C with this this pi differential. So this is a big group, a fine group. But if you're going
sorry,
to
João, just to clarify, so is this the definition of pi diff?
Exactly.
Okay.
Exactly. So yeah, and now pi diff, it's quite big, you know, and just like with the Galois theory, usual Galois theory, what you want to do, you want to splice it up into smaller pieces, and then you take one object, okay, you take one object, and you define subcategories by putting one object, then another, and this M, which I denote by M bracket tensor, so it's the category of, it's the smallest category of DE, which is generated by M and all its tensor products and duals and all that stuff. And once I do that, I get myself an isomorphism between M, the category of M, and the category of representations of our very dear differential Galois group. Okay, so of course this here is a theorem which you can verify in your favorite book. So say Singer van der Put, there's a proof of that, and so D Gal is just the usual Galois group that you construct, the differential Galois group you construct, and you can prove that this is the same. Okay, so I just recuperated, just reobtained my differential Galois group from this formalism, which will be useful point of view in order to advance in a more complicated basis. Okay, and of course, then if I go to the part B of the theorem, which I stated before, you just obtain the fact. Well, here it's because you know that the differential Galois group is algebraic. Okay, so. But in any case, because you have just one generator, then it just happens that the map that you get to the corresponding GLM is a closed embedding. So your D-Gal is a algebraic group. Okay, so now I move on to the theory over DVR, and so let me just fix some basic notation. So I work with the DVR, okay, discrete valuation ring. So if you don't want to work in too much generality, you are very welcome to think about things in this setting, okay? But in the beginning, everything works pretty well even in characteristic P, you know, so there's no problem there. So I take these notations and standard ones, are just Rn is just the truncation. And well, before going on, I just want you to present with a very simple example, which is the differential equation of the exponential. Okay, so, but now you make t depend on the ring. Okay, so t is a constant. Okay, and well, you have here the very simple differential equation, and what you do is just, okay, if you know how to compute differential Galois groups and you're working with t which is transcendent, okay, so well, at the generic point, then your group is just GM. Okay. Here I just didn't say it, but well, it's implicit that my space is the affine line. Okay. Sorry. So my group is just GM if I think of T as an element of my base field, okay, field of constants. So I do that, GM. But then if you truncate, okay, so you declare that T to some power is 0, okay, then you get the exponential as an algebraic function. So it means that your equation is trivial. So you have a solution, then the equation is trivial. And so what happens? So here you have a GM, it's a positive dimensional thing, and he's not seeing that when you reduce modulo T, what you get is algebraic, so it should be trivial. And the question is, what is the Galois object, which will explain this picture? Okay, so I need to see some group which will have, generically it's GM, but when I reduce modulo T, it's 0, or it's trivial. So here's the formalism. So I take X over R, smooth, scheme, whatever, variety, and I define the category of connections. So here I try to be a bit more general, and I defined using D modules. But well, that's just for giving me an opportunity to say that these things work in more generality, although I haven't done almost no work in greater generality than like ZP over fields of characteristic P. So in Galois theory, you cannot do much. Well, I can't. So you take the category of connection, integrable connections, which just amounts to D modules, okay? And you have the standard lemma, which tells you that a D module, a differential equation, is locally free, so it's really a vector bundle, if and only if E has no torsion. Okay, so of course, if you are over some space, then your module doesn't really need to be locally free over the whole space just because it doesn't have any torsion. But since when you restrict to a fiber of your space, it just turns out that you are locally free, okay, then life is much easier. Okay, so all you need to care about is if downstairs you have no torsion. So it means that if your module is not concentrated on some fiber. Okay. And then because of that, because of this very nice property, it just turns out that taking the fiber over a point gives you exact and faithful functor. And well, this is just right for the application of the theorem, okay, which is again due to Saavedra, but it's very hard to read off what's he doing in that big monograph. And so let me try to explain to you what the theorem says. So again, I have a category, some R linear category, which is also a category of R modules. Okay, so here I'm having a category of R modules. And I have my tensor product, which is associative and everything. But I have to replace the conditions that duals exist by the condition S, which is for Serre. So Serre spotted this condition. And so I have to replace that. Because of course, if you're doing stuff over R, okay, so it's more or less obvious that if you have R over T, this is not going to have a dual, or at least not the dual as a vector space, as a module, right? Having the good properties of a dual of a vector space. Okay, R over T, it's not a good dual, so it's the residue field. So you have to take that into account, and you replace this condition of existence of duals with the condition that objects can be resolved by something which has a dual. Okay, so this condition is true for group schemes, and Serre was the first to observe that, and is by no means true always, right? So it's not too hard to give examples where this fails in very simple contexts. And the conclusion is that there exists some finite, some affine and flat group scheme, whose category of representations is just T. Okay, so at the end you have the same theorem, and you need to take care of this condition of duals existing or not. So this can be a little scary because, well, you said, how do I apply this to construct differential Galois groups? And the good part is that you have this here. Okay, so in order for you to have something which is dualizable, all you're going to have to do is to take a sub. Okay, a sub of something dualizable will be dualizable. And that is a pretty strong condition, but that's because I'm working on a DVR. So a submodule of a free module over a DVR is also free, at least in finite rank. And this is the good property that will allow us to verify this condition easily. Okay, so now I make my definition. So I start with some E which has no torsion, so it means that it's locally free, and I define the D-gal just as this category. Okay, so the group that you obtain from your category of generated by E, right? So let me give you a potpourri of properties of this D-gal. So the generic fiber is the same, okay? So it's exactly the same as you would expect, so luckily. But here comes the problem. So this is the problem. It doesn't need to be a finite type. So it doesn't need to be an algebraic group. And that is because since E now is a representation of its own Galois group, right? So you have a representation here, okay? And just so happens that this is not closed. This doesn't need to be closed. So your D-gal does not need to be a finite type or algebraic over R. And well, then at the end, the definition of the big one, as I mentioned before, it's not so simple because the condition S may fail. Okay, so this one I don't want to touch much on it, but just want to prevent. I just want to warn you that it's not so simple. Okay, so let us go to the example. So you have this silly differential equation, right? So D-gal on the generic fiber is just a Galois group of the equation you do using the exponential. Okay, so this is pretty simple. And now comes the fun part, is that D-gal over Rn, okay, when I truncate this group, it just becomes the identity. And if you are used to things over DVRs, you know that the dimension of the fibers, at least when things are of a finite type, cannot grow like that. So you have a generic fiber which is of dimension 1, and you have special fiber which is of dimension 0. And this is telling you that your group is not a finite type. And at the end, what you get is that the ring of your D-gal is just this ring here. So this is what? I have my R of X, so it's, and then I start adjoining elements here. Okay. Oh, so here I forgot to put X to the minus 1 because it's a GM, but okay, sorry. Okay. So I need now to explain to you. So the conclusion I draw from the previous part is that these Galois groups, you can easily say to me, well, these are very complicated objects. There's no way you're going to compute with them. And so why are you insisting on this theory? And I tell you, yeah, there is one way to compute with them. And the idea is to use these neuron blowups. So there is this famous and very difficult paper to read of André Néron, where he introduces Néron models for elliptic curves and abelian varieties and all that kind of stuff. And one of the insights that he proposes is that by looking at blowups, okay, so in algebraic geometry you have blowups, and blowups are, you know, they've been around since Max Noether in 19th century, okay, so very important, very useful thing. And what Néron realized is that if you do not look at the whole blow-up, at the whole space of a blow-up, or you restrict your attention to one single chart, then you have what? A group structure being preserved. Okay? Because when you blow up something, then there's usually a Pn somewhere, and Pn is not a group, so well, you're in trouble. But Néron realized that if you don't blow up everything and you don't take the whole blow up, you're going to have a group structure. Okay. So let me explain to you what that is. So I fixed some affine group over R. And now if I have some subgroup of the special fiber, okay, then I define the Néron blow up as being by this ring. So say that your sub is defined by an ideal I, and then I just adjoin the inverse of every element in I. And this has been studied by a whole bunch of people. Okay, so it started with Néron, but then it was taken up by Waterhouse, and even in Langland's world, it shows up in the work of Prasad and Yu. And also, for my surprise, it also showed up in the works of people who are interested in things which are not really groups, and also in topology. So it's a very, very common object. Okay, then I go on because I have, so look, I'm blowing up something which is on the special fiber. Now I'm going to blow up something which is formal. So instead of working with G, I go to its t-adic completion. So I have my G, which is over some R, over some DVR R. And now I look at the completion, the t-adic completion of this guy. So G hat is now a group in some sense, okay? And instead of blowing up something on the special fiber, I'm going to blow up something which is a closed formal subgroup, okay? So these formal subgroup, if I truncate, they will give me subgroups over Rn, which are cut out by some ideal. And then what I do, I just put everything in there. So I start throwing denominators as much as possible. So basically the idea is that functions on my new blowup are made of functions on G, in which I start having the possibility to divide by the uniformizer if the function vanishes on H. Okay, so I have my functions on the closed part, and I say now the functions which vanish on the closed part I can divide by t. So I put this new function and so on and so forth. Okay, so this is So these are two types of blow-up. This is called the Néron blow-up. Bosch and these people call this dilatation, which is good in French, but it's a bit more strange in English. Dilatation, I don't know. Then when I blow up, things stays the same. Okay, so no change in the generic fiber. The Néron blow up, when you pull it back, when you look at the image, it's contained in H naught. So if you're used to blow-ups, whenever I present this stuff to algebraic geometers, this is the first part where they start yelling. And they say, no, well, what do you mean? Your blow-up is just, it ends up in just a smaller part. And I say, yeah, precisely. That's precisely the point of Néron, is that when you blow up, since you're looking only at one chart, you end up in the group H naught. Okay? So it doesn't dominate the whole space. And that was done for that. Moreover, the kernel of this map on the special fibers is an affine abelian group. As a not unipotent, it's just not really abelian, and this is marvelous. Okay, so what happens? What some people like to interpret this is that you take your group and you glue on your group. So you have a subgroup of some other big group, and you glue on the special fiber. You start gluing vector spaces. Okay. And this extremely nice property of the Néron blow-up of a formal thing says that when you complete the group, you just recover the formal group you started with. So this is a very nice property, which will show up later. So let me give you an example. You take GM and you take H naught given by, sorry, I forgot to say H naught is the identity here. So I blow up the identity of the special fiber. Okay? And once you blow up the identity on the special fiber, what happens is that generic fiber doesn't change. So here's the generic fiber. It won't change. And now the special fiber, what happens? It happens precisely as I said. What you do, you take the subgroup and you put a vector space on it. And now the special fiber, since I'm taking the subgroup, the trivial subgroup, and putting a vector space on it, I have a GA. So this is what people call the deformation of GM into GA. And now let me give you an example of formal blow-ups. And formal blow-ups are these guys. Well, so I start with the affine line, which is with this additive structure, and I complete t-adically. So what are functions on the affine line? They're just polynomials. And then if I want to complete for the t-adic topology, I just want the coefficients here to be divided by higher and higher powers of t. Okay, so this is this object, which shows in other contexts. And then I blow up the identity. Okay, so I'm giving simple examples. So I take the identity, but now it's the identity of the formal group. Okay, so I take the identity and then I blow up, and then again I have this sort of behavior. So the ring of functions of the blow up is just this thing here. It's functions on kx, okay, whose first coefficient is really an integer. So this strange ring, you could say. But my point in developing this theory is that you have these group schemes which can easily be non-algebraic. And my point when studying this thing was that they are non-algebraic, they are not of finite type, but they are produced by some well-defined method from stuff of finite type. So you see, I start with GA, which is a very simple thing. I started with the trivial group, which is a very simple thing. And by some process, I got a very, very bad group. But then you can say, well, he's not so bad because he's just the other ones and I'm doing some process on it. Okay. And why is it that this is a useful thing is that because they do appear every time. So what happens is that whenever you have a flat and affine group over R, in characteristics 0, okay, not true in general, well, I don't know, then what happens is that there exists some guy of finite type such that your G is this formal blow up. Okay, so it's just basically saying that no matter how ugly your group scheme is, not a finite type, very, very complicated, you can start from something which is a finite type. So here, of course, I forgot a very, very natural point, which is I have to have a fine flat and have a generic fiber which is algebraic. So really, then again, I have in mind a differential Galois group, and a differential Galois group is trivial is a finite type on the generic fiber, but it's not a finite type all over. So here, if I have something which is finite type on the generic fiber, then I just have that my group scheme is obtained by this process. So the idea of the proof is like that. So it's just happened that any G affine and flat will be a limit. So you take one group, you do an add-on blow up, and then you do another. So it's a projective limit of these guys. And I note that the kernels, when I go from one to another, they are always affine spaces. But I'm in characteristic 0, so affine spaces has no finite subgroups, well, other than 0. So it means that every time the kernel, it either grows or it's 0. It either is higher dimensional or is 0. But then these GNs, they have bounded dimension because I'm bounding the dimension by the dimension of the generic fiber, and they all have the same generic fiber. Okay. So the special fiber is growing, dimension is growing, but it cannot grow indefinitely because dimension is bounded. So at some point the kernels will start to disappear. Okay, and that means that you're blowing up always the same thing. And this is the same thing you're blowing up, which will give you the H, which I mentioned here. You know, this is the H, which I mentioned. Okay, so now I move on to the structure of the Gal, and I want to know what this guy is. Okay, and so again, my simple example is this one. It's the d-gal of this differential equation. And the conclusion is that as a module, remember that the ring of functions here was polynomials with coefficients in k, such that the first coefficient, the constant coefficient belongs to R. So this is not projective. So in terms of module theory over DVRs, this is pretty bad. And then you have strange behavior like that. So the strange behavior says that, for example, you take this representation here given by this matrix, and this representation is the identity modulo all t's, but it's not the identity. So it's a very strange property. And my point is, can I rule out this sort of thing from the differential equation? And the answer to that is a property which we call the prudence. And prudence is like that. So it means that you have to avoid the following behavior. Say you have a representation of G, okay? And then assume that you have a line inside of V. So this is free, okay? So this is a free R module which affords a representation of G. And then say that you have a line inside of it. And that when you reduce modulo T, this line becomes invariant. by the group G. Okay. Well, I want to rule that out. I want to say that if this line is invariant, then L itself is invariant. So basically, quickly saying, if something is invariant modulo T for all T, then it has to be invariant itself. So some sort of completeness property of invariance. And then you prove the theorem. So if I have this property, then my group is projective. My ring is a projective module. And so the main application of this, so here is the reference to the paper which we wrote. So it's on the structure of fine flat group schemes. It's the second part. And why can I use this thing? Is that if X over R is smooth and proper, then the ring of the differential Galois group is projective. So it means that this guy here, this sort of thing here, will not show up because, of course, my equation is defined on an open variety. Okay, and then the next step you're going to ask is, oh, okay, what happens if I have regular singularities? And so we're going to get there. And the proof is just the algebraization of sheaves on proper schemes. Okay, so that's it. Okay, so now I want to do calculations, and maybe the oldest. So it's question mark. That depends on how you read history. The oldest way of computing is by analysis. So let me recall what people call Schlesinger density theorem. Okay, so but in a more general form. So if I take a variety which is projective, okay, so a compact curve, and I take some divisor with normal crossing, so take out some points on your curve, and then I have an algebraic connection on the open part, okay, and I say it's regular singular. So what regular singular means, this is also a head herring, but well, let me just be lazy and say that I have an extension which is logarithmic. So it means that on some local charts, my connection forms, my differential equations will have just dx over x on the denominators. Okay. So then the theorem of Schlesinger, okay, which you can read off Deline on this slide. So he proved this thing also, but in a different light. So you have your complex space. Now X, which is the open part, is a complex manifold. So I can have a monodromy representation. And the theorem is that if I have regular singularities, then the Galois group is just the image of the monodromy representation. Okay, very important theorem, allows a lot of calculations, at least when the analysis is simple. Okay, then you can always argue that analysis will be very complicated usually. But then you have this theorem. Okay, so now you try to do the same thing, but on the context of C double bracket T. So you introduce the usual the notation. So instead of X, a variety over C, you want something over R. You take out the divisor. You can think of a curve over R, a projective curve over R. You take out some points, and now you're going to reduce modulo T to obtain these schemes, okay, these curves. And since Rn is of finite dimension over C, I have analytic spaces. So I have analytic space Xn, Yn, okay, and Xn without a bar. Okay. And Deline, he proves that over the analytic spaces, okay, so this is called the relative Riemann-Hilbert correspondence, okay, over these Xn, which are analytic spaces over Rn, so remember Rn is a finite dimension over C, so Deligne proves that if you have a connection, then the sheaf of horizontal sections of the analytification is a local system. Okay, so it's a local system of R modules. So at the end you have your curve, you made some points on it, but your curve depends on a parameter. And Deligne saying that if you have a connection which is relative to R, okay, so it depends on a parameter, then what you're going to get is a continuous family of local systems. So you can define the monodromy of an object by taking the limit. So for each n, you have a representation of this fundamental group, and then you pass to the limit, and you obtain a representation. So, and then the theorem here is precisely that you have an equivalence. Okay, so if you take the category of regular singularities and you go to this monodromy thing, you do this monodromy equivalence, this monodromy construction, then you have an equivalence of categories. And let me finish by a calculation which has a surprising answer, at least for me, was surprising. So you take a very simple setting, just take P1 and remove 2 points. And you consider this very explicit differential equation, okay? So just a constant Euler differential equation. So I have a regular singularity here and a constant stuff here. Now I reduce modulo t to some power. So I mean t now is something which to the power n equals 0. So I can compute monodromy just using the usual functions, and the monodromy is this one. And then at the end, what happens is that this thing here, it lies on, so this is an abelian part, oh sorry, this is a GA, so this is a copy of R, and this is a GM, excuse me, so this is a GM, and this is a GA, okay? And I take the graph of the exponential function, which is formal, and the d-gal of this guy is this blow up. Okay. So to conclude, I'm just saying that these d-gals, they appear, so these groups which are not of finite type, they appear very naturally on, even in GM, in P1 minus 2 points. So you have to deal with them. But this means that this H here, okay, this H here is a subgroup which is formal, but it's not algebraic. So this is a very subtle thing, that if it appears in such a context, then H is transcendental. It means that it's really formal, but not algebraic. And with that, I conclude. Thank you.
All right, thank you so much for this very nice presentation, João.
Thank you.
Do we have any questions or comments? Please feel free to just unmute yourself and ask, but you can also type it in the chat.
And let's see the chat.
Okay, so maybe in the meantime, let me ask, can you go back to the main theorem that you just had towards the end?
Sorry, I just which theorem?
Not more towards the end. Yeah, this one. Yeah. So what exactly is the assumptions on R here? Does it need to be the formal power series over the complex numbers?
Yeah.
Okay, just for this one. Okay.
Yeah, because at the end you're doing analysis, you know.
Yeah. That was basically my question. I mean, there is really analytic, like there is no, like it probably doesn't even make sense to ask if there is like a purely algebraic version of this theorem somehow.
Yeah, you could imagine, you know, you would get a purely algebra, because you can say that this theorem at the end, I'm throwing stuff under the rug, because this theorem, what it's saying is the following, is that once you have a connection on your variety, okay, so this is why Deligne is showing up here, okay, so because Schlesinger, it's much older, but then you have, I put Deligne's name here. So why is that? is that because Deligne, he proves the following. If you have an equation on an open variety and you have some boundary, okay, then you can push the equation to the whole variety by putting regular singularities, okay? So this is Deligne's theorem, which is saying that you have an equivalence between equations on the open part, which are regular singular, and you have this extension where you put the exponents in some place, okay? So this is the canonical extension, as it were. And this makes sense over any ring of characteristic 0, okay? And so it was the work of Baldassari, André, and now Mauricio Caiotto in that monograph they wrote, this Geram cohomology or something, right? And then they tried to give an algebraic proof of this theorem, okay? And so from what I know, there's a mistake somewhere. They corrected it, but it's not trivial. It's a difficult theorem. And but you could ask, is this true also in this context without being overseen? And the answer is I don't know, and I can prove it the way Deligne proved his theorem, because I follow his methods here. I don't follow André and Baldassari. So everything I do is I take Deligne, I understand it very well, and then I pass.
Yeah. Okay, thanks. So another question, this condition S you mentioned earlier,
Yeah.
which somehow generalizes the existence of duals. So you said that like somehow if the category is tensor generated by one element, it is fine, but somehow if you take all of the modules, is somehow this condition is not fine. So how can that be somehow?
Yes.
Like why does it fail in general?
The answer is that we don't know if it fails or not. So basically, take any scheme, any A1 over R. Okay. So now my question is, if I give you a differential equation which depends on t, but it can depend on t, meaning that t is not there, okay? Can you find me an equation which has no torsion, which depends on t, and has no t torsion, which surjects into your equation? So you have a module which is concentrated on t equals 0, okay? Now I want you to give me a differential equation which maps onto your differential one. Then you can say, yeah, of course, over C double bracket t, you can do that, because what you can do is that if you have t equals 0, okay, then you just consider the same equation on the free module, and you declare that t equals 0 because so. Let me try. Hard to explain that without a blackboard, but so let me say it. Okay, let me do it over characteristics P and characteristics 0, because now it's going to be worse, and maybe I can communicate the idea. Say that you have a differential equation characteristic P, a D module in characteristic P, which is this thing that Van der Poot and Matzat use called a iterative differential module. Can you lift it to characteristic 0? And the answer is no, you can't. Right? So it doesn't mean that it's going to be a quotient of something which is in characteristic 0. And that is the problem. So you cannot put them all inside one same boat. So was it?
Yeah, thanks.
Yeah, so think of the Matzat Van der Poot stuff, iterative differential module
Yeah.
in characteristic P. So question, can you find something in characteristic 0 which lifts that one? So the answer is no. Okay. So then if you want to do something for the whole affine line, or even if you want to puncture the affine line, then you're in trouble.
All right, if there's no other questions or comments, then let's thank João again.
Thank you. Thank you.
And so I'm looking forward to seeing everyone again next week.
Okay. Thank you. Thank you, man.
All right, thank you. Have a good
Bye-bye.
weekend.
Thanks
Bye-bye.
Bye-bye.